So let's do one more dynamics problem with Newton's third law, right? That uses it. So we've done a pulley and horizontal, right? Moving it horizontally. We've done a pulley that's vertical. Sorry, not a pulley horizontal. It's just motion with a string horizontal. One with vertical. How about half and half? Right? What do I mean? So let's tweak this a little bit even more and connect a pulley this way, right? So I have let's go back to our good friends like 3 and 2, right? 3 kilograms, 2 kilograms of mass like this, and find same thing, find the acceleration and find the tension in the rope. Okay, so use a better pen and let's see if it's clear on the board. Not really, but you know what I'm asking. Yeah, so how do you do this? And now I think it's going to get really repetitive, so I'm just going to jump right into it. But there's just a the additional subtlety is how to deal with horizontal and vertical like this. The key thing is to recognize how they accelerate. So think ahead a little bit, what will happen if you release it? If you release it, well, this guy, well, let's draw the free body diagram, right? So this guy is easier. It's touching the rope, so there will be a tension and there will be its weight. That's the only thing it's in contact with. This guy is in contact with the string, so I'll have a tension over here. And I think at this point, we've done enough times that this T is the same as this T, right? And if you still don't know, try to retrace the steps. Why is this T the same as this T? And the hint is take this rope, stretch it out, okay? So draw a free body diagram, take the rope that is connected at an angle, stretch it out, draw the free body diagram and go through the arguments again. I'm not going to do that. Otherwise, it's going to get really repetitive and boring, but make sure you understand that. And we're just going to accept this. Does it have friction? Well, if it does, then you will include friction. If it doesn't, you don't have to include friction, all right? So let me, by completeness, do include the friction over here. Because we could have a problem with friction and we'll see how that works. Now, is this a kinetic friction or a static friction? Well, it depends if it's moving or not. So let's say it is moving, it's sliding around. So there's a small kinetic friction to sort of dragging it back, okay? So if you want to solve it without friction, in any of your equations later, just take a little f, set it to 0, and then you'll get the result without the friction, okay? All right, yeah, so step 1, you got your free body diagram for each. Okay. So as you can see, another tip is once you begin to gain more and more confidence, you can draw the free body diagram directly on the object. Okay. If you're not separated out, it will always still be helpful that way. Okay. Secondly, what do? You write down Newton's second law. Okay. So we're going to do that, right? So for A, and again, now it's almost either repetitive or just reflexive at this stage. You want to label these guys A and B so that I can actually put in a label A and MA equals to the net force for B like this. Okay, what's the net force on A? Now I need the direction. Okay, so which direction should I choose? Now, let's not choose the standard XY, because if you're clever, we're focusing all on one-dimensional problems at the moment, if you can tell. This does not look like a one dimension, but it is. If I stretch this out to here, you see that actually, well, this is actually going this way, this is going this way. I can stretch this out and it's essentially motion along one dimension. It does not, unlike, for example, the counter example is a projectile motion. It's genuinely in 2D. You cannot draw a straight line. You cannot easily draw straight lines that connects every single point, right? But this is possible. And this time, let's do, by the way, if you do XY, that still works, okay? But I'm gonna show you the smart way. You can try it yourself, the other way, the brute force way, right? So I'm going to choose this way as positive and this way as positive. Why? Because I know, at least without friction, this is going to go down this way, and this is going to go this way. So the acceleration, I'm going to call this A, and this guy is also going to accelerate with A, okay? So what I'm really saying is, this is the acceleration of B is A, in positive A in this direction, and the acceleration of A is positive A in this direction, right? So now you should be able to convince yourself the magnitudes are the same because it's inextensible. You can go run through the same argument as the previous video, right? But for labeling purpose, once you gain some familiarity, you can just say the acceleration of this guy goes this way, acceleration of this guy goes this way, okay? All right, now we can go and plug that in. So which way is positive? This way is positive. So the net force on A is going to be positive T minus the friction. That's going to be this minus this, right? The net force. And the net force on this guy, on B, is going to be W minus T, like this, okay? You might wonder, where does gravity go over here? Yes, gravity goes here, but it's counteracted by the normal force. This is not accelerating in this direction, so we don't have to worry about the y direction of that. We know that all the acceleration is in this motion and this motion. Okay, so now it just we just have to plug in all the numbers. 2a equals to t. I don't know what that is. Let's solve. Yeah, I'll keep that as well. And this is 3a. Because it's going down this way in my positive direction. For example, you can always double check the acceleration is the same direction as W and opposite to the direction of T for B. Is that true? Yes, the acceleration is the same direction as the way I label it. It's same as W and opposite of T. So this is all consistent. So W is 3G, right? mg, so 3 minus T. And let's solve it without friction, okay? So this is, I'm going to solve it without friction, and I'll leave it as an exercise for you to solve it with friction. So without friction, you see it's these two equations. Now, should I add or subtract them? I have a t over here, a t over there. I can, this t and minus t, let's add them, right? Because if I add them, this will get rid of this. So if these are not nice numbers, you can do substitution if it's easier, whatever. But the rest is just a math problem, and this is 2a plus 3a, and then on the right is 3g, which means 5a equals to 3g, a equals to 5/5 of g. What is that? Well, that's 6 over 10g. Again, I could plug in 9.81, but let's just keep it in terms of g. So that's 0.6 g. So that's the acceleration of these guys, right? So this is moving at 0.6. Isn't it interesting, right? If I drag it horizontally, if I did it vertically with the Atwood machine, what did we get? It was 1/5 g, right? Or 0.2. It was 20% of the gravitational acceleration due to gravity. And here it's 60%. It's still not 100% because there's something holding it back. And what's holding it back? It's not friction. I've not cared about friction. What's holding it back is the inertia of this guy. It's causing some inertia, even if this is a frictionless, zero friction surface. All right. I'll leave it for you to find the tension. I've done that in advance. I think I got the tension is 1.1 G, right? So if you put G equals to 10, so that's roughly 11 newtons that you have to support. So you can double check that. But really what I want to leave as an exercise for you is to solve what if I have mu K, the kinetic coefficient of friction, is 0.5, right? So remember what that means is we have a formula for this. Friction is proportional to the normal force. So you need to, I'll leave it as a challenge for you, right? To find the normal force, and I'm saying that's 0.5, that means this is the kinetic friction coefficient, which means the friction force is half, in this case, the surface is going to create half of the force of whatever the normal force is, okay? All right, so you can redo this and tell me what is A and what is T. And also as a quick second thought as well, instead of me doing the same thing and filming a separate video of this, which I was just about to do, but let's do something different by calculating to the answer for this. I'll leave it for you guys to figure it out. Once you've done it, either put this on Piazza or put this on the comments below, either way, and we'll see if we can rely on the collective intelligence of human beings to figure this out, because this is how real world works. When you actually step out of the classroom, there's no sort of official answer to look at the back of the book or any official solution manuals for you. And the best you can do is find some people with similar great minds, and you can have similar knowledge. You use your collective knowledge and figure some problems out, and see if each other got the same result, and there's no sort of God-given answer. So let's do something different. Let's try that. So let's try this approach this time, and we'll see what we can come up with.